Okay. Thank you again for the chance to be in Irvine. The weather is always expected to be nice. So I will switch the plan a little bit after discussing with Yifeng. Well, today I will tell you about the cell problems, but I will tell you right away the new results on non-conversion of the vanishing viscosity process, because it's rather natural in this flow. So that in the third and the fourth lectures, I can tell you about new results on quantitative homogenizations. I will start slowly with the basic theorem of Lyon's perpendicular and Baradan that we talked about yesterday. I will give you a quick proof, and then I will go to this one, which is quite exciting. I'll tell you the history and why it's interesting. Okay, so let's start with this basic thing that we mentioned about it yesterday. Again, for many experts in the audience, this is kind of like by now very standard, but it's also good for some of you who have not seen it. The thing, okay, let me call this one ergodic problem at P. The thing about this equation, as noted yesterday, is that it's not monotone in the unknown, right? So it has already many solutions. I'll give you one example. That already you can see V is a solution, V plus 1 or V plus a billion is also a solution. So to approximate, to approach this kind of problem, then a natural way is to introduce monotonicity in the sense that I take for lambda greater than 0, I consider the people in the literature call this one the discounted problem. I will see if I have time to explain to you, maybe not today, why it's called the discounted problem. That I let the equation to be monotone. I consider lambda v lambda of y plus h of y b plus d v lambda of y equals to 0 in Rn. I consider this problem. And because of this factor, the equation now becomes monotone in lambda, and I can have comparison principle, again, this is an analog of the Laxmi-Brown theorem. When you have this zero order terms coming in with lambda greater than 0 or lambda large enough, and the equation becomes monotone, and you have a unique solution. Okay, I'm not proving this, but there's a unique solution v lambda. Yep. Okay, let's observe basic properties here. Is that you can see that if you shift the Hamiltonian by an integer vector, you still have the lambda v lambda of y plus h of y plus k b plus d v lambda would still equal to 0 for all integer vector k, right? Because these two Hamiltonian are the same, right? And this means that by uniqueness, again, it's very basic, but you can see that by uniqueness, you can see then that v lambda y plus k, which solves this equation, is also equals to v lambda of y. Right? We solve the same equation. So of course, this means that v lambda is Zn periodic. So that's the first thing. And the second thing is that you can also have basic a priori estimate. Then you can, construct sub and super solution with this equation to have basic bounds. The simplest thing to do for this kind of equation is you can just take constant and see what's going on, right? You plug in constant. If I plug v lambda to be a constant, then I would have lambda times c plus h of y b plus 0 equals, well, less than or equals to or greater than equals to 0, right? So you can see easily that, okay, say that you set c naught to be the L infinity naught of h of in y of p in L infinity of the torus, for example, and then you would have minus C naught over lambda and C naught over lambda a sub and a super solution to the equation, right? I mean, it's just this basic calculation. And because of that, you do see that because there are sub and super solutions, so you would have minus C naught over lambda is less than or equals to V lambda less than or equals to C naught over lambda, or equivalently, you have that lambda V lambda is bounded. Okay, let's put this one in our okay. And because this one is bounded, you have the Hamiltonian acting on P plus dV lambda is bounded, right? Again, everything is very loose. Yes.
For the back. You can see. Okay.
Can you see? Okay. Okay. I'll try to write a bit quicker. Okay. And here's the point that I need to use coercivity, right? Coercivity comes in, and by coercivity, that I have that P plus dV lambda is bounded. Constant depending on C naught and on H, whatever, but anyway, I'm not gonna specify the constant, but I have dV lambda is infinity is bounded by a constant. So I have two a priori estimates here. And like yesterday, when you asked me a question, if I don't have coercivity, then in fact, it could be dangerous, right? I might not have the cell problem defined. For the G equation with divergent-free vectors here, then there is no cell problem. The cell problem might not have solutions, but you can still have homogenizations. But in other setting like cutoff curvature G equation, there can be no homogenization. Or yesterday, I just saw last night, is it true? That there was a post by a paper solving a problem asked by Yifeng and Jack and Mooney, that for the some other kind of Hamilton-Jacobi equation, I forgot the name now, that also you don't have homogenizations if you don't have coercivity. So now it's moving very fast. So just a post last night. So okay, anyway, so I have that. Okay, so now from a priori estimates, I can pass the limit, right? I'm now using the fact that V lambda is periodic, so everything can be shifted back to the cell, right? Everything can be shifted back to the cell y equals 0, 1 to the n. Any point y here is of distance at most root n to 0. So what I have now is I do have V lambda of y minus V lambda of 0 is bounded by dV lambda at infinity times the root n, which is bounded. Right. Yes.
So what's exactly the definition of C0? It's L infinity and Y.
Yeah, L infinity in y. P is fixed.
So it depends on P.
Yes. All this V depends on P. So for now, I'm writing it not dependent on P, but later on. Yeah, P is fixed, absolutely. But all this really dependent on P.
Okay.
Yeah, absolutely. Thank you. Okay, so I have V lambda, this one is bounded, right? And of course, the gradient of V lambda of y minus V lambda of 0, this is just a constant, so it's Q equals to the gradient of V lambda of y less than or equal to C, then I can use Ascoli theorem, right? So everything is up to this moment, again, it's very basic. That there exists a subsequence lambda j goes to 0 such that I would have, let's say that V lambda of j y minus V lambda j 0 would converge uniformly to V of y. Again, I omit, I mean, every V here actually depends on P, but for now I'm omitting it. I'll bring it back later. And again, this one is also bounded, so you can say that lambda j v lambda j of 0 is conversion to a constant minus c in R. And as a matter of fact, okay, so I have that conversion. Yeah, those conversion that are important for me. Okay, so now I bring everything together. I have the existence of the cell problem easily, and I'll prove uniqueness afterwards. So okay, so let's write out the cell problem again. I have lambda j v lambda j at y. I now subtract v lambda j at 0 plus h of y p plus dv lambda j at y minus v lambda j at 0 equals minus lambda j v lambda j at 0, right? I have this one converges to a constant c as lambda j goes to 0. I have that this one surely converges to 0, right? Because this one is less than or equals to lambda j times the L times dv lambda j in L infinity times root of n. So this one converges to 0, right? So and okay, my stability of viscosity solution as v lambda j y minus v lambda j 0 converges uniformly to v lambda vy. So like in Yandan's talk, so that we use a lot of this sort of stability and touching from above and below, that we have vy solve this equation that yp plus dvy equals to c. Okay, and because this is periodic, so it's defined in a torus. As I said yesterday, I'm going freely between the torus and Rn. Does that make sense? So that exists until very simple. And in fact, you can see right away here that I have to use crucially the property that I'm in the torus. For example, when I'm not in the torus, when I'm not in the compact setting, things can get crazy. And there are people here who work on the random setting, Yifeng or Paul, or others, that it can be very complicated when we are in the random setting. I don't have time to go to that, but okay. So I have this. So I have existent, right? So existent is done. Done. Let's now prove uniqueness of C. Okay, I don't mean uniqueness of V, but uniqueness of C. And I'll give you example soon. Okay, uniqueness of C is that this ergodic constant is unique, right? This is typically, so C is sometimes called additive ergodic constant. Sometimes it's named that. But let's prove uniqueness. The proof of uniqueness is by contradiction, right? So assume otherwise that there exists V1, C1, V2, C2 with C1 less than C2 such that I have two equations, h of yp plus dv1 y equals to C1, which is strictly less than C2, equals to h of y equals dv2 of y in the torus. Okay, and let's say that v1, v2 are continuous function in the torus. I mean, they are Lipschitz, but okay. So again, as an analyst, whenever you have some room, whenever you have some wiggle room, you're gonna squeeze in something, right? As I know that from the beginning, these equations are not monotone in the unknowns. But because I have some wiggle room, I can squeeze in something. Okay, how do I squeeze things in? So there exists some delta greater than 0 small enough. such that, okay, let's say delta times the L infinity number V1 plus delta times, okay. L infinity number V2 is less than C2 minus C1 over 4. Some wiggle room. I'm just gonna squeeze in some delta. Okay. Because I can squeeze in this delta, so I have delta V1 plus H of Y P plus dV1 is less than now C1 plus C2 over 2 or something, less than delta V2 plus H of Y P plus dV2. Okay. And now these two equations are monotone in delta, right? I have the comparison principle. From here, I would have V1 is less than or equals to V2. Okay. So this is always my favorite question to ask you guys. How do I get a contradiction from here? Why is it a contradiction? Do I claim that this is a contradiction? Question is why? It's always something to ask. Okay, I give you 10 seconds when I'm writing down the next thing. Now, just what do you think? Why do I have a contradiction here? Anyone?
Because you can always add a constant.
Yes. I'm not asking you, but I'm kidding. But yes, we have experts in the room, so they are laughing at me. If V1 is a solution, then V1 plus a billion is also a solution, right? By this logic, I always have that V1 plus a billion is less than or equals to C for any constant C. Does that make sense? Yeah, so that is a contradiction. Okay, yeah. Thank you for it. Okay, so now let's talk about this thing. So I am now going from the 87 to 2026. 40 years. Yeah, 40 years. So now I'm gonna tell you some fun thing about this problem. So this is a result that we got just this year. Yes.
So can you get from this some continuity of C on P?
Yes. Okay. Yes. Okay. Yes. So let me write it down, and then I'll tell you what is done. Okay. Yes. So let's consider this Hamiltonian for even simplicity, right? So thank you, Eric, and thank you, Paul. So let me now write out the cell problem. Let me also tell you what is done, right? So the cell problem is that for all P in Rn, now there exists a unit number. I can name it H bar P to be in R, such that the cell problem, now let me write it this way, even for this quadratic form, 1/2 P plus dV y P. So I'm putting P in here to show the dependence, minus Vy equals to H bar P in Tn equals to Rn mod Cn as a solution. Okay, so this is the classical mechanic Hamiltonian, and actually it's good to write like this because it's more explicit. Okay? So what do we have? So in this convex setting, remember, yeah, some of you asked me yesterday, do I need homogenization and all of this? Do I need convexity in the periodic setting? No, everything is, I only need coercivity and periodicity. Now I'm switching to the best setting that I can, right? So I can see the classical mechanic Hamiltonian. I have that this is going from two variables, right? Space and momentum. After this sort of change of variable, I end up with h bar that only depends on momentum, so it's kind of integrable, right? Okay. So yes. So in this convex setting, yeah. So like what I asked, in this convex setting, we do have that h bar of p surely is continuous in p. And in general, it's always continuous in P, but also that in this setting is convex in P. Um, however, in general, H bar has flat piece, has a flat part in general, part at minimum of H bar. So what is interesting is that you do this sort of homogenization process. You start with a quadratic Hamiltonian. I'm sorry, I draw it. Quadratic Hamiltonian. Fix y. Your Hamiltonian is always quadratic, uniformly convex. I'm making it worse. So after homogenization, you would end up with some Hamiltonian like this. That although it's convex, there's a flat part here. So to this day, even understanding the shape of the flat part is quite hard. You know, in 2D is, I think I can say at this moment it's fully understood, right? With some Yifeng. But in 3D higher, understanding this is challenging. That's the first thing. The second thing that so what is this? The information of the flat part. The shape of this. Understanding it deeply in 3D or higher is still totally open, I should say. There are some results by I think Burago, Ivanov, and Kleiner. Some other results, but overall it's just open. Okay. The other thing I want to mention to get to this non-convergent result is, which is quite severe, is that in fact, there are two things, right? We have examples that the first thing is that we show that P mapped to V of Yp is not even continuous. If you think about this as sort of some change of variable, in terms of KM theory, you would need lots of differentiability, but we have examples in 3D earlier and in 2D now that this map is not even continuous. Okay, of course, you know, and I should say that the fact is also that there can be many solutions VYP to the cell problem. So the cell problem has many solutions, and that's why it's quite challenging. So let me focus on one example, which is exactly our goal to do it here. So let's now consider P to be equal to 0. I'm even fixing now P is 0. And dimension is 1. Okay, I'm even coming to the simplest setting or simplest possible setting. So for P equals to 0 in dimension 1, and for simplicity, I write V of y 0 as just V of y. Okay, so my PD is now in ODE, right? So 1/2 V prime square y minus V of y equals to h bar 0. Or you can name it just constant C, either constant. Okay, yes.
This like this V, the solution of this problem is not unique. What do you mean by E going to V of 1?
Yes, so So there, yeah, good point. Yeah, so that's why I said I'm cheating a little bit. There doesn't exist a selection of V such that this map is continuous. So whatever selection you do, you don't have continuity. Yes, okay. Yeah, okay. So thank you. So very good. Okay, so now let me do this computation with you. Okay, yeah, so now also gonna focus on a simple case of V, of the potential of V, that the map, the graph of V gonna look like this. So it's one periodic. One. So it has two wells, two kind of essentially symmetric wells. In my drawings. It's two wells like this. I'll specify it later, but for now the graph of V looks like this. It has two symmetric or more or less symmetric wells of 0 and 1/2. I want to solve this equation. Okay, very simple. So I have minimum of V is equal to 0, and I claim that the constant C is equal to 0. Okay. How do I claim that the constant C is equal to 0? I'm just going to solve the equation, right? So I'm going to solve the ODE, simplest ODE that I can. Here is 1/2 V prime Y squared equals to C0, so capital V of Y. Okay. Well, to solve this, I'm just going to take the square root, right? So this is equivalent to V prime of Y equals to square root of 2VY, meaning that you would have V prime of Y equals to plus or minus square root of 2V1. As simple as it is, right? Of course, you need to have some compatibility condition, right? So the compatibility condition is that you need integral from 0 to 1 V prime of Y dy equals to 0, right? Because it's periodic, right? Okay. Well, it's symmetric, so I think that we can guess the solution, right? So we can guess. Okay, you can get some solutions. Some are obvious, some are a little bit less obvious if you are not used to. Oh, wait, okay. Thank you. Solution. Okay, let's do some solution. Maybe I'll stop here. That color is a bit hard to see. Okay. Some solutions, let's just draw the graph and see. How do we see the solution? Y, this is little v of y. Well, the easiest thing I can go is that I can let V prime is positive here and negative here, right? Because it's kind of symmetric, right? So positive here meaning it goes up here, plateau here at 1/2, and then go down. 1. Okay, not bad, right? This solution should be C1. Right, because at this point, I mean, it changes sign here, but at this point, square root of 2VY is equal to 0 for Y equals to 0 and 1/2. So it's okay when it changes sign here, here, and here, right? And of course, you can flip it that, right? So you already show you non-uniqueness because the downward is a solution. Okay. And you can take this one, you ship it out. This is also a solution. Because you see that if shift V by any constant is a solution, right? Okay, so let's call this one V1, this is V2, this is V2 plus any constant, right? What is also striking about this, like in Yan talks and others, is that when you take minimum of two solutions, it's a solution. V1, V2 plus K is also a solution. Okay. So this one is also a solution. Yeah, so there are many solutions. So that's why KM theory doesn't hold in the large setting. You have some sort of change of variable. The goal with KM theory is sort of to interpret KM theory, understand the invariant set, and see what kind of invariant structure that is still being kept. But anyway, that's another story. I don't have time to go to that. Yes.
So why can't C be the maximum? So C needs to be chosen so that in this case, so that we take the square root of this.
Yeah. Yes.
So it could be the maximum value of B also.
Yes, depending on cases. It has to be unique. In this case, it's indeed the minimum.
Oh.
Yes, and in the convex setting, thank you. So in the convex setting here, I do have this formula. I have H bar P equals to this similar to the principal eigenvalue formula. I have infimum of P equals C1 or C infinity is the same, and maximum X in R of H of Y P plus dpy. I have this sort of formula. It's some compatibility formula. Yeah. So you can see that from this sort of formula that indeed you can take the maximum value possible here, but then you have to take infimum among all possible choices. So it's exactly like the principal eigenvalue formula for elliptic operator. Right. Okay. So that's that. And what is interesting here is that there's so many solutions. Again, there's some invariant structure, the so-called Aubrey set of matter set hidden in here. I don't have time to go to that. These 2 points, in fact, in the Aubrey set of matter set, I only want to make one observation. It's going to be useful for us. Observations here that if V is a solution, V can only have its minimum at 0 and or 1/2. So it can only change the value, the branch from negative to positive or positive to negative at 0, 1/2. So all of this can be solution. I would say local mean whatever. Okay. Yeah. All right. So now let's go to the non-conversion. I think I have enough preparation to go there. Of course, I need to be mindful of my time as always. Okay. So now let's go to, so this is a very important open problem posed by Jocelyn Price Moser in 1999, by Craig Evans in early 2000s, by Anataraman, Iturianga, Sanchez Mugado and others. Okay, so maybe let me say that this is an open problem posed by Jocelyn Price at UCLA at the time, Moser in 1999. So we discussed with Paul Rabinovitz. He said this was the time that 1999 Moser passed away. Christ was a numerical analyst at DRI, right? So it's numerical analysis for this sort of problem. And Jocelyn, we sent a paper to him. He's happy. He's a son-in-law of Moser. So it's interesting. I mean, this is all through Paul Rabinovitz. He helped us to connect the dots. Okay, so the open problem by Jocelyn Price Moser, let me say it in this sort of language, and then I'll tell you exactly when they formulated that. Is that we look at the ergodic problem with epsilon here, that if I add viscosity, so I would have 1/2 V epsilon x squared minus V y. Vy, I have Laplacian, so minus epsilon v epsilon y equals to h bar epsilon 0, or you can just call C epsilon in the torus. Okay. And as epsilon goes to 0, you have this ergodic problem, E, which is 1/2 Vy square minus Vy equals to h bar 0, or you can call C in the torus. Okay, so the question posed by Jocelyn, Price, Moser, by Craig Evans, by Anantaraman, Ituriaga, Sanchez Mugado, and others, including Yifeng, Diego Gomez, Hiro Yoshimitake, and others, that we ask this sort of question is that in the limit, do we have unique selections as the viscosity vanishes to 0? This is a very natural selection problem for all of us doing PD, right? And because when you look at the problem, with viscosity, everything is nice, supposedly. So when you pass the limit, do you have a unique selections? Because I just show you that the limiting equation, there are many solutions, right? So this is a selection question. Okay, let me normalize it so do I have V epsilon of y minus V epsilon of 0? Because you see that everything can flip around by constant. So I'm normalizing it by constant. Does it converge uniquely to Vy uniquely as epsilon goes to 0? So that's a selection problem that people ask about. Again, it's a very natural problem also. I mean, when people do mixing, right? So Tarek or others also do mixings, or you can also think about it in a fancy way when you try to do vanishing viscosity. When Navier-Stokes to Euler, you have unique selections in case everything is smooth when you have all solutions that are possible. Okay. Does that make sense? The questions? Okay. So now let me tell you the story about Jocelyn, Price, and Moser, that they started looking at the problem. That in fact, in their paper, they look at the exact formulation, but they didn't look at Hamilton-Jacobi equation. They look at Burger's equations. Okay. So they consider Burger's PDE. First, they assume that, okay, so let's say that first they assume that they look at the forcing. I mean, no, V is the potential, Vyt, that is Z2 periodic. And they look at the equation that they do, okay, let me write V, so maybe W epsilon T minus W epsilon X equals minus epsilon W epsilon XX equals to V X of XT in the torus cross R, and they look for periodic solutions. Okay, so they look for, okay, let me write out D squared. They look for periodic solutions because it's forcing is periodic in space-time, and they ask the question is that as epsilon goes to 0, do you have that W epsilon converge to W uniquely, where W solve the normal Burger equation, Wt minus Wx equals to Vx of xt. Okay, so that's the question that they ask. It's exactly the selection problem. Okay, one thing that I need to clarify, a lot of you are gonna ask that, okay, this is confusing because Kruskov and others already proved you have uniqueness of the entropy solution in the conversion, right? So this is different because this is not a Cauchy problem. You don't prescribe initial data, right? This is periodic solution. Okay. And then Jocelyn Christ Moses simplify the problem a bit further. They say that, hey, to simplify the problem, I'm going to look for V that is independent of time first. Okay, and V is independent of time is exactly this problem. Okay, but let me explain a tiny bit more why why this constant comes in here. Right? Let me explain a tiny bit more. Okay, so let's work on this here, right? So you see that this term, and this term, they are. Oh, I'm sorry. These three terms are in divergent form, right? So when I integrate with respect to x, they're gonna go away, right? So what I have is that I have conservation d over dt integral into torus v or w epsilon dx is equals to 0, right? Because all the other terms goes away. So that means that I would have integral in the torus w epsilon of xt dx is a constant. And this constant turns out to be exactly this sort of constant c epsilon. And similarly, I do have integral in the torus w xt dx is a constant. Okay. And then Jocelyn, Christ, and Moses simplify the problem a little bit. They say that for simplicity, let's look at the case where Vxt is just V of x. Okay. So when you look for Vxt is just V of x, then you do end up with this equation. The t goes away. Wait, I'm sorry. I should put plus here. I'm sorry. Good. So I have w epsilon x minus epsilon w epsilon x equals to v of x, right? And in 1D you can see that conservation law is equivalent to Hamilton-Jacobi equation. The way that you see that is that you write this one, everything is in x here, right? You differentiate everything in x, so this is equivalent to 1/2 w square minus epsilon w epsilon x minus v all differentiated in x equal to 0, right? And then you write w epsilon is equals to v of x, v epsilon of x. Then what you have here from this equation is that you have 1/2 v epsilon of x square minus epsilon v epsilon x minus v is equal to the constant, which is c epsilon. That's what is.
So we are just thinking about the steady solution.
Steady solution. Yeah, okay, yes. So this is in the spirit of what Tarek talked about yesterday, right? Because we search for special solutions. So steady. The simplest solution you're always looking for are steady solutions or periodic solution of time. I mean, those are the key objects that we always try to search for patterns, right? We look at good patterns. Okay. So let me right now state down the theorem, and by the end I will give you I think that is a very important open problem from APZ people. Okay, please remind me to say that open problem when my time is over. Otherwise I forget. Okay, so let me right now state the theorem. Theorem 2 for today. This is by with Jiren Liu in Shanghai and with Yifeng here. So I mean, because we people from viscosity solution theory, I mean, Crandall's and Evans family, the key thing is that when you do vanishing viscosity, the expectation for a single equation is always you have conversion. And you have unique conversion because that was one of the key things from viscosity, right? Viscosity solution is that you have unique selections because because you know that is how the solution was named viscosity solutions. So I think that Yifeng was aware of this question when you were grad students, right? You wrote some papers on that from 2000 to 2005. I was also getting involved with this when I started my PhD in 2008. We have been dreaming of this question, thinking about that for a long time. So eventually we have the result, and unexpectedly the result is negative. So that's why we cannot prove it, right? So if you try to prove something for so long, if you cannot prove it, then maybe count the examples and do this. Yeah? So we say that there exists a potential V, okay, can be as smooth as you want, CK in the torus. It can be same thing, but for PD people, CK is okay, such that V epsilon of Y minus V epsilon of 0 as epsilon doesn't converge to a unique limit as epsilon goes to 0. So that's a theorem. Okay. So okay, I don't have time to tell you everything, but I will try to tell you some of the key ideas. Oh, wow. I have 10 minutes. Okay. Yes. Okay. All right. So yeah. So normally in a summer school, let's see. I should explain well, but today I'm a little bit sketchy because I want to tell you some of the exciting and interesting ideas. For the next two lectures, I'm going to go carefully into some of the details, not this, but some other thing. Okay, so let me tell you some of the key ideas. The key idea is that in order to prove non-conversion, we need to create instability. And the creation of instability is actually not easy, and it's hidden behind the fact that, okay, I'm going to call it, this is the effect called dancing between the two wells. 0 and 1/2. So we need to create certain instability so that in some way our solution gonna dance between the two wells 0 and 1/2 in certain ways. Okay, the way we do it is that, okay, we're gonna define V of X to be okay, the wells are the same in the second in the quadratic expansion 1/2 X squared, but then it's going to be different in the higher order terms. So A times omega square root of X. Wait. Well, let me see if I can write it a better way. No, I can write omega. I can write square root in later. Okay, yes, I can write omega. Right? X to the 4th power. Okay. So for X near 0. And we define V of X to be 1/2 X minus 1/2 squared. So you see that the quadratic behavior of V near the two wells at the set, they only differ in the higher order term. So I make minus A here. So A is a positive constant. X minus 1/2, X minus 1/2 to the 4th, or X near 1/2, and then it's smooth and positive otherwise. Okay, so V looks like this. Okay, so here omega of R is defined to be sine of log of 1/R. Okay, so this is where we did need some of the help from ChatGPT. So when we have some idea, it did help in sort of designing some good functions. one of the key property that we need to use here, I don't have time to go to this, is that one of the key technical point that we use here is this thing that we have omega of square root of epsilon times z, which is, let me write down, sine of log of 1 over square root of epsilon times z. This is equals to sine of log of 1 over square root of epsilon plus log of 1 over z. This is equals to, I mean, this is a leading order term, so it's omega square root of epsilon plus little o 1 or fixed z not 0. Okay, and I'm sure that some of you here, I remember, for me, I remember vividly when I started my college, I did my first year when I have to consider all this kind of function, whether they are differentiable or not. I hated them, like oscillatory, right? But you know, it turns out to be useful. Because it was like, why do we care about x cubed times sine of 1 over x, right? What is the class of ck that is in? Did you do that kind of homework problems? Yes, we all did, right? Okay. So we consider this kind of potential that is oscillatory. Okay, so now let me, yeah, my time is very limited, so let's see what's it saying. So some of you asked me yesterday that why do I consider this quadratic Hamiltonian, right? And also that why does it matter? So let's write it down. I'm gonna try to convince you I use V, right? So V epsilon y squared minus V epsilon y minus Vy equals to C of epsilon. Did I go to C epsilon? Yes, C epsilon in the torus. Okay, so the key thing for this quadratic Hamiltonian is that we can do a Hopko transform to move from the quadratic viscous Hamilton-Jacobi equation to a Schrödinger operator. So we are now moving to exactly understanding principal eigenvalue of a Schrödinger operator. So I let phi epsilon to be e to the minus v epsilon over 2 epsilon. Okay. Let me check.
Yes. Forgot epsilon in front of the second order thing.
Yes, thank you. Did I forget it here? Okay, I have it. Okay, yeah, let me check because normally I would do the computation with you, but now I might have it. Just I think it will be correct. Yes. So if I define P to be like this, you do your computation. What you end up there is that you would end up with minus 2 epsilon squared P epsilon y. Okay, minus V of y P epsilon equals to minus C epsilon P of epsilon in place. So you would end up with this Schrödinger type operator. It's exactly the Schrödinger operator, right? So you call this one, you call P epsilon equals to 2 minus epsilon squared d squared over dy squared minus V. Then you have that P epsilon equals to minus C epsilon phi epsilon, right? You look at here, phi epsilon is positive. So this tells you that minus C epsilon is the principal eigenvalue of the Schrödinger operator equations. Okay, so far I have not done anything crucial yet, and my time is about to end, so maybe I can just finish. But so let me tell you maybe 2 key points without proof. Key point number 1 is that how do we see the sort of the dancing effects of the Schrödinger operator? Here is the fact that when we look at this Schrödinger operator, when we zoom in near the 2 wells, we're going to see the dancing effect. So let's zoom in at the 2 wells. So let me call the Dirichlet eigenvalue at 0, epsilon is the Dirichlet eigenvalue, the principal Dirichlet eigenvalue. Of E epsilon on the interval minus delta to delta, so small delta. And I call AB 1/2 epsilon is the principal Dirichlet eigenvalue of E epsilon on 1/2 minus delta to 1/2 plus delta. Okay, so I can see that the Dirichlet eigenvalue here. So meaning that this is a local argument. I want to see what happens, not everywhere, but only near 0. Okay, only near 0. So let me write it down, and then you will see the dancing effect, and then I'll write out the next plan that I can prove that it can explain. Okay, so I have this. So the key point is that I have the Dirichlet eigenvalue U0 d of epsilon is equals to, that is given to me here through this formula. That is here, right? So the Dirichlet eigenvalue of this is I have that is equals to epsilon plus 3 I omega squared of epsilon times epsilon squared plus higher order terms. Okay, so the Dirichlet eigenvalue near 0 is of this form. But the Dirichlet eigenvalue of D near 1/2, I mean, but it's of similar form, right? I have the minus size. Okay. And the Dirichlet eigenvalue here tells me that there's a switching effects here because omega, remember omega is the highly oscillatory terms. Along one sequence, it can take value 1, the other sequence, it can take value -1, right? So what I do is that there are two subsequences, epsilon n plus and minus goes to 0, such that I have omega of epsilon, square root of epsilon n plus is equals to 1. And omega square root of epsilon n minus is equals to -1, meaning that in one sequence I have E0d of epsilon n plus is going to be greater than E1/2 d epsilon plus minus some C0 times, or plus some C0 times epsilon square, and along the other subsequence is greater than E1/2 epsilon minus plus C0 epsilon square. Okay, so it's oscillatory, so it's dancing around in one of the sequence that the energy near the well 0 is bigger, but in the other subsequence the energy near the well 1/2 is bigger. Okay, so now let me just tell you the key point 2 and I end. Point 2 is the so-called localization effect. So this is sort of very interesting effect coming from semi-classical analysis is that if in one sequence, if the wells is preferred here, because you see that in this case, the energy in this well is lower, right? When it's preferred here, then most of your energy of your principal eigenfunction is focused on this well. Because the principal eigenfunction is always choosing the place where the energy is smallest to stay. Okay? So the localization effects here says this. So I have P epsilon of U epsilon equals to minus C epsilon U epsilon, where U epsilon is the principal eigenfunctions that the L2 norm is 1. Okay, and we say that along a sequence, epsilon goes to 0. It's indexed, but I'm lazy. So that if the energy as the well 1/2 is it's bigger than energy at the well 0. So if the energy at the well 0 is smaller, right? Then in fact I would have that most of the energy is concentrated at zero. So U epsilon at zero as 1/2 is less than C times e to the sigma over so it's exponentially k. Okay, so what it says is that in this case I have two, well, 0 and 1/2 here. Most of the energy is concentrated here. Wait, yes, okay. Oh, I see it's about to be done. Okay, so most of the energy is concentrated in this well because it's exponentially k here. So in other words, from here you can have that U epsilon square dx as the probability measure will converge weakly to delta Dirac at zero because you're focusing all of the energy on the lower well. Okay, but for the other subsequence, I have that it's conversion to the other delta Dirac, and hence I have non-conversion. Okay, so it's a very interesting dancing effect that you create this dancing effect by creating the higher order perturbations. The higher order perturbation allows you to dance around and along different subsequences. You would prefer different wells. And because you prefer different wells, then this sort of this thing can actually call a matter measure that you choose different wells to stay. So it's instability in the wells. So that gives us the result. So let me end by giving you an important conjecture. There's a good at poets here because so I think that this is about KPZ. I think that it started from Sinai. Of course, this is from Komogrov School, right? And then Konstantin Kanin told me this conjecture that I think that this is written in the survey paper by Bakhtin, Jury Bakhtin and Kanin. That you consider exactly, I mean, it's the analog of Jocelyn Price-Moser. What you do is that you do in 1D. So 1D in space and 1D in time. You consider exactly that kind of equation that you have, let's say W epsilon T plus 1/2 W epsilon X square minus V minus epsilon W epsilon XX equals to V of XT. Okay, and you assume that V is random, stationary ergodic, and let's say that is unit range dependence in both X and T. Okay, for those of you who are not used to probability, that means that you are in the space times here. Let's say if you are in this block or in this block, you are totally dependent. So it's unit range dependent in X and T. The conjecture by Sinai, Kanin, and Bakhtin and Kanin is that they conjecture that you should have almost everywhere. The probability that W epsilon converge uniquely as epsilon goes to 0 to W is 1. And that will solve the equation. Okay. Because we talked with Costa Kanin over this summer, he said that this kind of perturbations is not generic. So it's there but not generic. So he said that the events that this doesn't hold is still having probability 0. At this moment, I'm leaning towards that is wrong. But who knows? I mean, this is a huge deal. If it can be done, it's a really huge deal because I mean, if you write this one in terms of Berger equation, it's the KPZ equation. minus epsilon, you go to the tensionless KPZ. It's a huge change. Okay, let me. I'm sorry today, I'm very sketchy.
So in the original case, V was assumed to be like analytic or and only has finitely with critical points and something like that. Do you think the answer would be different?
Yes, so thank you for that. So in terms of Berger or Hamilton-Jacobi, CK is a more natural class. If you do analytic, then this perturbation doesn't work. This work in CK or C infinity. What we need to use here, technically, I didn't say that it didn't have time, is that I have epsilon square here, or even epsilon to the power infinity is okay. This one is always dominated by exponential decay, but that's okay. So technically, CK or C infinity is the same. Analytic, I don't know. Indeed, in the paper by Jocelyn Kreis-Moser, when they wrote it down, indeed they consider first analytic. They have one proof that they have conversion. I don't have time to go to that. Is that if you have two wells or many wells, but if one well always have lower energy, then we have conversion. In this case, we don't have conversion because in the quadratic term they look the same. That's why we use instability to have non-conversion. So in that part, when Jocelyn Kreis-Moser wrote it down, they only consider CK or smooth enough functions. So yes, Kalin also asked us like, how about analytic? I think analytic is a very good question. It makes a lot of sense. I don't know. For us from Hamilton-Jacobi, like Evans and Ataraman and all the other people that people often consider like C3 or so that's one thing. So great. And the other thing is that I didn't write them down because I have some examples, but they are not too too deep yet. Is that you can from here you can create some same philosophy. You can create some situation where you consider, let's say, system of Hamilton-Jacobi equation or system of conservation laws with Cauchy data that you have non-conversion, meaning that you have different subsequences converging to different limits when you do vanishing viscosity. So that shows that for a system Hamilton-Jacobi equation, there's no way you can give a good definition by doing vanishing viscosity. However, I don't like them yet because the system I have to do is a little bit artificial. People can always say that, yeah, for conservation law, people can always say that it's artificial, or sometimes this kind of viscosity you add is artificial viscosity. Sometimes you want to add physical viscosity. Right? So it's always one way or the other. But at least what is surprising to us is that in 1D, for smooth potential and for single equation, we don't have conversion. This is sort of like never expected. I think, like we tried really, really hard. And Barry Simons and others also wrote papers in this directions. There's a fancy paper named do you feel a flea on an elephant? Flea on an elephant here is you have this potential. This is an elephant. You perturb it a little bit, not exactly at 0 or 1/2, but you perturb it a little bit here. So he called it a flea on an elephant. But it doesn't go in this direction. So I would say that this kind of thing is very, very deep in spatial theory, right? So the last thing I want to say is that if you ask me, I would say that Yifeng and I and Jiran discuss a lot. And I tend to believe that this sort of phenomenon is quite universal. In order to create instability in higher order terms, this is quite universal. Whether it's going to be useful in other contexts, I hope so. Hopefully. Let's see.
Yeah.
Yes.
Oh, so this is like a super broad synopsis kind of question, which is that I guess I'm understanding that we kind of just solved this solve problem, basically kind of like a weak camp problem. Problem. And so the effective implementation is good. Just to make sure we're just understanding that, or we show that this is the unique critical value
Yeah.
of the shit of that.
Yes. 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 In this case, you can see, for example, in this case, when I do this Hopko transform, for the case with Laplacian, this one is unique, and minus CF1 is indeed the principal eigenvalue of this elliptic operator. So it's very natural. Of course, I mean, I can only do Hopko transform for the quadratic case. Then you can ask the same for general equations. But as also as I said, I have some examples that I'm not yet very happy. Is that I can do it for the Cauchy problem with initial data, but again, they are made up. This is not made up. This is sort of very natural. It comes from. Yeah, you.
Just a quick question. So the multiple transform is the same transform that relates the reverse PD to the problem from the.
Yes. Yes. The name of the game is that whenever you have quadratic in the nonlinearity, it can always be absorbed into the Laplacian. When it has to be quadratic.
Oh.
Yeah, it's always this name of the game. Yeah. And that's why it's by coincidence that you see all this sort of phenomenon, right? You also see in direct talks yesterday about the Schrödinger type operator. So it's I would say it's very simple, but yeah, quite interesting.
Maybe one more question? Oh. No? Thank you for very interesting talk.
Thank you.